Thank you, everyone, for having us over here. Um, so this is one of the vendors and sponsors session, but I'm going to keep it technical. I won't do any products, and I hope you would like it. So I was at a Lenovo conference last Thursday, and I gave a similar sort of presentation. It was in Bangkok and mostly attended by pre-sales engineers in the ASEAN region, and I had to ask them if they had heard of Mellanox or have they worked with Mellanox before. So I believe I don't have to ask that question over here. Everybody is familiar with Mellanox in this region. So I'm going to ask you a different question. Have you guys heard or seen this book or know about this book? No, right? I didn't expect you to. So it's basically, it's for all the people who are interested in the biology of Drosophilas. There may be some, simulation uses over here. But again, that's not the reason why this book is famous. It's actually a pretty good book, but also it was famous maybe 6-7 years back, when a postdoc from Caltech wanted to buy this and went online to Amazon. And this is what he saw. He saw that the book was listed as, used from $35 and too new from 1.7 million and 2.19 million. So he was kind of taken aback. And he thought, okay, I want to buy a new one, but let me check it the next day. So he kept on checking and checking, and the prices wouldn't go down. I mean, it went to 18 million, went to 23 million, and it was really, surprised. What was happening was, it's like the robot price war. I mean, this is welcome to machine learning. As in 2011, they had a simple, the two sellers called Profnath and Bordybook. They had a simple equation saying that, my price will be equal to y equals mx plus c, some multiplier times the competitor's pricing. And if you look at the pricing on various days, it was always following that particular pattern. So there was, and it's a good thing for them that the product of these two was greater than 1, so it went like this. If the product was even slightly less than 1, it would have gone down to 0, right? But yeah, jokes apart, I mean, this is, it's nothing to do with machine learning as such, but yeah, people back in 2011 were doing these kind of things. And now it's very much a reality. You see Facebook's AI supercomputer on the top 500 list, it's at number 31. And NVIDIA's AI supercomputer is on number 32, which is a pretty powerful computer. Of course, it's not doing the standard, M1, M2 into C kind of equation. It's doing much more than that. But these systems are very powerful. They are based on GPUs, and one thing that they have in common, the top ones, that they run high performance interconnect now. They're not the loosely coupled systems which you used to see, which used to do big data analytics. Even they gained quite a lot using high performance networks. But earlier Hadoop systems were supposed to be loosely coupled, running over gigabit Ethernet, right? And now they all are like supercomputers. So with that, I'm not going to be talking too much about machine learning, but I will talk about some inherent technologies in the interconnect that is going to, give boost to these kind of machines in the future. Before I do that, I'll just, again, this slide I took from my Lenovo presentation. It's because in that region, many people are always saying that, okay, now there is a lot of competition, and of course, InfiniBand is declining. So I just wanted to put that thought to a rest, that it's not exactly declining. This is the latest top 500 list. And whether you take the top 100 system, the top 200 system, top 300, of course, there's going to be competition, and it's good to have healthy competition. But InfiniBand still by far outranks, any other interconnect which is out there. So it's not declining, and all in all, actually, it's coming into more and more non-HPC applications, just like AI and machine learning that we talked about. So with that, let me get into what I'm going to talk about in this presentation. I'm going to talk about Mellanox's outlook. What do we see? I mean, the title was, future of high performance interconnect. So what do we feel and what do we see the next generation of interconnects would be doing, apart from just increasing the speeds and feeds? And you might be aware of this, but we are talking about a data-centric, offload architecture. You're all very much aware of the onload versus offload pitch that Mellanox has. So I'm going to dwell a little bit into what do we mean by offloads. Of course, we talk about RDMA. RDMA can be done in hardware. RDMA can be done in software. We are always the proponents of doing it in hardware. And similarly, now we are talking about doing some amount of computing in the network. And mind you, I'm not talking about doing, especially after yesterday's talk, I'm not going to be doing floating point operations inside the network. But what I mean by in-network computing is data that can be processed close to the network in a more efficient manner should be processed close to the network rather than being run as a C code inside your kernel or user space. So we need to analyze data or process it as it moves. I will give you an example of what we are doing in the HPC domain, but it kind of flows through in all the domains that we are talking about. So what do we do here? So of course you're aware of Mellanox doing adapters, Mellanox doing switches, Mellanox doing smart NICs as we call it, and even FPGA based, well, not FPGA based adapters, but adapters that have got some amount of inline computing. So in all the domains, so let's say you talk about HPC, we do RDMA offload onto the NIC. We do MPI tag matching offload. We do GPU direct. We are now doing even NVMe over Fabric. So NVMe is a new protocol on storage side where we'll be offloading many of the target computations onto our NICs. Talk about security. Let's say a data center wants to do, let's say Monash wants to do IPsec. Now, instead of running IPsec as a code onto your kernel space, what if all the data that was coming in was encrypted and decrypted on the fly as it enters your NIC? So we are running IPsec inside our NIC. Okay? And you can run the standard algorithm, standard keys, or you can even have your own keys. It's programmable. You can do that. So what it means, there are two things here. First of all, you don't take any CPU cycles for doing IPsec. And second, it's not a software code that is running. So it is completely disassociated from the kernel and user space. It's running in the hardware, so it's more secure, right? So like that, there are many other, products that we're doing. I'm going to be specifically talking about some things which are more relevant to the high performance computing industry. And we call it SHARP, Scalable Hierarchical Aggregation Protocol. And we'll kind of see one or two uses of that. Again, this was inspired by yesterday's, making numbers great again. So I said, let's make interconnect smart again. So what we're trying to do is, we're trying to do some operations inside the switch itself. And let me tell you what kind of operations. Consider MPI collectives. Consider MPI reduce operation, for example. Okay, what happens in a reduce operation? You have a rank, a head node, a head rank, which is going to collect data from all the other ranks, and it is going to apply a reduction function. The reduction function can be as simple as MPI add or MPI, or some things like that. So if in a standard computer, if you want to do that, it's always done in software. So there's a head node which will try to gather data from everybody, and then it will apply the reduction operation. Now, in a 1,000 rank job, gathering data from 1,000 ranks means you're getting it serially one after the other from each and every physical node. What if the reduction was being applied as and when the data is being collected? And that's what we're talking about when we say in-network computing. So giving a practical example, let's say you have an InfiniBand cluster which has got, a leaf spine topology. There are, 18 or 20 switches connected to a leaf, and like that there are multiple sets of nodes connected to a leaf. And one of those nodes is the head node, which now needs to gather all the data to do a reduction. Okay. Rather than collecting from everybody, what if the switch, which has all the 18 servers connected, can do this reduction operation and give the result to the head node? If you can do that, it means that all the leaves can actually collate data, reduction data, and give you the result, and the head node just sums up the result if the reduction was MPI sum. So this can give you a tremendous amount of boost, right? And it actually does. So what I explained over here is, okay, before I go there, so it actually does, but now you're going to ask, how does it, kind of help you in an application? So let's, profile an application. What I explained is over here, you have multiple ranks, and the ranks have a particular, matrix, and the reduction operation is just the summation of all these elements of that matrix. And we are able to do it in the switch as and when it is flowing. Where will you be able to use this? Well, take any standard application and do a profiling. I've just taken the most common weather application, WRF, right? If you profile that, you see and you break the MPI communication in its elements. For example, how much was a broadcast, how much was reduced, how much was all gather, how much was standard, send receive. Then you'll see the green one over here shows the reduction operation. And I've just taken reduction as an example. I mean, we can offload many collectives, and with newer and newer technologies, we're going to be building more and more offload capabilities in our switch. So in reduction, you can see that almost 20% of the time was spent in reduction. And the reduction was not ranging across all sizes. It was basically just 8-byte reduction. This basically says how many percentage calls were used for what size of the data, and you can see 100% of the reduction operation was actually 8-byte data, the green line over here. So if you have a very small, processing unit in the switch, which you can have, then you can do these collectives very nicely inside the switch. And when you do it, this is what you get. So if you had, all reduce run and as software, then the latency that will be there for finish a certain reduction is almost 3 to 10x compared to what you would do in the hardware. So this is, now again, when I say 10x in the hardware, doesn't mean your application is going to run 10 times faster. Or what it means is this slice over here will get reduced 10 times. So if your overall compute to communication ratio is, let's say, 30 to 40% of compute and 60%, 30 to 40% communication and 60% compute, then that 30%, 20% is going to reduce 10x, which gives you around about 10 to 15% boost in application performance. Again, this is specific to this application. There are many other applications where you do get much better improvements, but you'll never get something worse than what you're getting with the system. So this is just like a performance booster in your network. Consider, we talked about a lot of applications. Consider there are many solvers which solve in the Fourier domain. Okay, when you do solve in the Fourier domain, you're going to do an FFT. When you do an FFT, there is always a matrix transpose. And when you do a transpose, there is always an all-to-all communication. So we can actually boost all-to-all communication as well. That has nothing to do with the in-network computing, but there are many other engines in our network which kind of boost all those things. So it's not just this green pie over here. There are many other pies that we are trying to improve, because we believe just by increasing the speeds of the card, you will not get much advantage. Of course, you will get some, but there is much more to be done in other domains. With that, let me go into Okay, I have enough time. So let me go into RDMA. We talked about GPUs. We talked about GPU RDMA. We see that when we use GPU RDMA, there is huge amount of benefits in the latency and the achievable bandwidths again. And it's pretty straightforward. I mean, there's nothing nothing very complicated about it. Consider a system. This is a node which does not have GPU RDMA. How does data flow happen over here? So your NIC card is basically, it's an IO device. So it is mapped as a memory device onto your system. So it's able to it's able to use some part of the system memory. Similarly, your GPU is also mapped on as an IO device to your system, so it is able to address a certain physical memory range. When the data comes inside, it goes through the chipset, it goes through the CPU, and it is written on to the memory which is pinned to your NIC card. Then there is a code which is going to copy this memory from the physical location of your NIC card into the physical location which is addressable by the GPU, and then the GPU will be able to read it and put it on its own memory. So there are actually 3 times data copying that is happening, right? If you're able to do GPU RDMA, the NIC card can directly write onto the GPU memory, and that's what is supported in CUDA 5 onwards. So with CUDA 8, you get all these things automatically. You don't have to change your applications. If you've written for CUDA, you have GPU RDMA. And this GPU RDMA does not just run on InfiniBand. It can run on RoCE enabled, it can run on Ethernet network as well. It just needs to be RoCE enabled. And people use this. It's not, again, we've been talking about it for quite some time. We also talked about GPU sync, where the control plane processing is also now done on the NIC rather than being run as a code inside your driver in your kernel space. People have been using it. One example is Google, which is public, with TensorFlow. What they saw that they can do with RDMA, they can do almost 2 times faster, TensorFlow, and these are all results published by them. Again, there are 2 flavors of TensorFlow. One is TCP based, which Google has outsourced, and then there is one which has native RDMA, which is actually not made public. I think maybe Google wants to keep something up their sleeves, but you can use an RDMA framework like gRPC to run TensorFlow on top of it and still get all the benefits. So I'm talking AI because many people are there from the universities, and they don't want to be using their HPC systems just for doing high performance computing. They want to be doing some amount of data analytics and also machine learning. That's where, if you have an heterogeneous system, you can take advantage of all the goodies that we bring in onto our interconnect and benefit all different type of users, not just the HPC users. It is being used. It's been used at scale. This is an example of Baidu's self-running, self-driving car initiative, where they made a big machine learning cluster. Paddle is Baidu's framework, equivalent of TensorFlow for doing their AI, and this is pretty much like the Monash cluster, Blair. It's actually a 100 gig RoCE enabled cluster which uses GPU RDMA, and it has got 16 Tesla K40s in a single node. And like that, it has got around 150 odd nodes, I believe. So it's a pretty big system. It contains a leaf-spine architecture with Mellanox as Ethernet. Again, it doesn't mean that Ethernet works better. That's why they're using it. It may be because their network guys were more, I would say, familiar with Ethernet, or they wanted to do Ethernet over here. But it works as well. It works actually better on InfiniBand because it's native RDMA. But that doesn't mean that if you're using a open stack kind of environment with Ethernet, you can still use it. So these are few things. Let me talk the other new thing that we have. This is basically the socket direct technology that we talk about. Again, in GPU clusters, you can do GPU RDMA. I think everybody over here knows you can do GPU RDMA as long as the NIC card shares the same root complex as the PCI slot in which your GPU card is residing. Now, to get more and more GPU cards, you will have PCI slots from the other core. And if you're, let's say, putting the NIC on one of the CPUs, which has its own integrated root complex, and if you have a GPU on these PCI slots, on the PCI slots of the other CPU, then you will not be able to do GPU RDMA. So one workaround is to use two cards, but you have a better option now. You can use a card with socket direct technology in which the card actually sits on two PCI Express. I mean, you get two benefits here. First of all, people ask me, okay, you're talking about HDR. When you do HDR, you're going to do 200 Gbps. When you do 200 Gbps, there is no PCI Gen 4 right now. So how do you take out 200 gig from an X16 Gen 3 slot? Because the slot itself is limited to 128 Gbps. So one thing you can do is actually you can put this socket direct card. It is by 32 Gen 3, so you can actually take out 200 Gbps. The other thing, you can avoid QPI altogether. Now, mind you, when you're in the current generation systems, your RAM is not connected all to one CPU. You have a NUMA architecture. You have RAM connected to CPU 1, you have RAM connected to, you have 4 channels with CPU 1, 4 channels with CPU 2, and every time it doesn't mean that the processes are only going to be accessing the RAM of the near core. They might need RAM access from the far away core, and that's where the QPI will be shared. And if you have a NIC card which is connected to only one of the CPUs, then you will be using the shared QPI. If you use a socket direct card, you have QPI which is not in the picture now. All the processes going from any of the CPU cores will get same kind of latency and same kind of performance, and you will be able to use GPU direct if you have an heterogeneous environment. So this is something which solves 3 problems, actually 3 problems that I talked about. Firstly, the 200 Gbps bandwidth, how do you take it out? Secondly, how do you avoid the QPI bus altogether? And thirdly, you can do GPU direct using these cards. So with that, I'll just come to the only product slide that I have. This is what is there in the future. Well, it's very near future. We have ConnectX 6 running at 200 Gbps per port, which can use what I showed in the previous slide. We have this quantum silicon, which is a 40-port HDR switch, and it can also do 80 ports of EDR. So I will talk a bit about that. And then, of course, you're aware of the spectrum line on the Ethernet side. There are higher speed switches coming up in that domain as well. There are our LinkX transceivers and the HPCX library that we talk about. So again, it's not all marketing and presentation. There's the real switch. So this is, you can count, it is 40 ports. So this is the actual HDR switch. And this is how the front panel is going to look like. There are 40 port link and activation LEDs on it, and you see there's something called lane A and B. I mean, it's pretty much, so why is it here? What it means is every port is capable of splitting into 2 EDR ports. So in effect, it is a 80 port EDR switch. So we've made, the radix is now 80. That opens up a whole new possibility on what kind of topologies and what kind of networks that you can design around this. I'll be glad to talk about various network topologies that are now feasible with this kind of radix, and you can do very nice flat meshes. You can do well, I don't want to be talking competition here, but you can do Dragonfly better than Cray now with this kind of a radix. Okay, and again, did I have anything more to tell about this? I think this is it. We'll have it by the end of this year. So you can start designing with HDR. And I'm not saying you design with HDR if you don't want 200 gig right now because you're not saturating the per node 200 gig, then do EDR to your nodes and do HDR uplinks. That you can start designing right away. And with a radix of 80, actually you can do 3200 port in a 2-level factory. So a system as big as NCI actually can be made using just 1U switches in a 2-level factory. You don't have 3 levels now. Now Suda is going to hate the engineers because he needs to sell double to make the numbers, because now you have 80 ports in this switch, right? So again, there are various possibilities that exist around these switches. Let me, how are we on time? I think we're pretty good. Yeah, we've got 5 minutes. So let me just talk about something which is dear to me, interoperability. Okay, and I think I had maybe some, gone through this with some people. So we talk about standards. So it's a nice cartoon. We say there are 14 competing standards, and now the industry gets together and says, "Hey, that's too many. We gotta do something which is good for everybody." And bam, you have the 15th one, right? Well, it's complicated, but it is required. But you need to have an outlook of having backwards compatibility, and this is something which is very, very important for users. As a user, I myself, 8-9 years ago, was always into that. I don't want to throw away my hardware. I mean, it's not the network geek in me who's speaking, saying that, hey, I love seeing the uptime on my switch, and I want this switch to last forever and ever. But there are scenarios in which you have, let's say, a FDR-based storage, and it's a 10 petabyte storage that you invested into, and now you put a EDR or an HDR-based compute, and you want to connect the storage. If you don't have backwards compatibility, you end up putting tons of LNet routers, right? And the LNet router is going to have FDR switch and FDR NIC and an EDR NIC, and it's going to do the routing. Okay, but in InfiniBand, thank God, you don't need to do that. You don't need to have these LNets. You need LNets for any other thing, but at least for this, you can actually natively connect everything to the newer technologies and natively mount your storage, your older storage, and no need to change. Now, we always have this vision that, this outlook that all our technology should be backwards compatible, and that's why we put in lots of thoughts on how we're going to do it. One, I'll give you, this backward compatibility needs to be on the file layer, on the link layer, on the transport layer, everywhere, right? So I'll give you an example of the file layer. How do you increase the speeds? InfiniBand, you saw on that switch, you saw the connectors. They were QSFP standard connectors, right? And your InfiniBand port is a 4x port. Per lane, it had certain amount of speed, and it has 4 lanes on it. A QDR had 10 gig per lane, and you had 4 lanes, so you used to get 40 Gbps. FDR had 14 gig per lane and 4 lanes, you used to get 56 Gbps. What about 100? You saw 100, it is 25 gig per lane, you get 100 Gbps. Okay, what about 200? So there are various ways. I'm just going to talk about technology here. How do you increase the interconnect bandwidth with the available technologies? What you can do is, let's say you can increase the per lane speed. Right now we are at 25, you can go to 50. Okay, you can go beyond that. You might hit the limits of copper and signal integrity on the boards, while 50 Gbps means 25 gigahertz signaling, which means the third harmonic is at 75 gigahertz. You're running microwave onto your boards, right? So it becomes difficult. Or you increase the number of lanes. If you increase the number of lanes, you will not be backward compatible. Then you need to have some kind of a gearbox mechanism. I mean, let's say you make 200 Gbps with 8 lanes, and you have EDR with 4 lanes. How do you convert? So you need to have some big gearbox, some more active components. So increasing the number of lanes on the electrical side, not a very good idea. What else can you do? Increase the change the kind of coding. Right now we do non-return to 0. That means a 0 is a 0, a 1 is a 1, right? What if I could code 2 bits and use something like pulse amplitude modulation? Electrical engineers out here would know it. It's a very basic thing in communications theory. You encode, instead of having 0 and 1 as 2 levels, you can have 4 different levels in your clock or in your data waveform. If you do that, then you increase the speed, keeping the line rate, the baud rate constant, okay, and keeping the same number of lanes. You can also do multiplexing on the optics side. I mean, telecom industry has been doing it for decades. You multiplex more and more, and you can, the fiber is capable of running more and more wavelengths. So what I'm trying to say here is there are lots of ways of doing it. At Mellanox, we have capabilities of expanding in all these directions, and we can run 200 gig and even 400 gig out today. Okay? So that is something that we can do right away, and we are doing it keeping complete backwards compatibility. Now, again, I don't want to specifically talk competition, but this is one place where I personally, it's not a Mellanox remark, but I personally don't like, OPA, is they're not keeping backwards compatibility, okay? Which I feel, for users is very important. So I think that's about it. I didn't want to spend too much time on various, technologies. At the end of the day, there are many. Again, they look like sheer marketing slides where you say, oh, this much better, this much better, this much better. But believe me, there are applications. I mean, I myself ran few 2 weeks back, weather applications, and I could see that there are, whatever we talked about, the collectives, offload and all that, I could see 10 to 15% differences. And all you need to do is you need to run it along with the HPCX package that you have from Mellanox's OFIT driver. It may not work readily with Intel MPI, which everybody is used to using. But if you are seeing lower performance, definitely get in touch with us. We can even give you the flags that you need to set on Intel MPI that will ensure that you don't get poor performance. You'll get better only. And definitely if you use HPCX, which is utilizing all the internal offload capabilities of the silicon, then you will see performance boost in almost all the applications. And well, you will not see it on embarrassingly parallel applications, but you would see any application doing FFT, doing all-to-all, any applications which has a majority of MPI collectives, specifically reduce, gather, scatter, you will see these differences. I think with that, I will just finish my talk here. We're pretty good on time. And this is what I have to summarize. Open to questions. Thank you. Okay, so we're pretty good then. Okay, so if you have anything else, I'm over here, and we can definitely talk. Thank you.